Hello, I'm Granger. So this talk is about, or this paper is about still to video face recognition. So the main challenges there are domain shift between source and target domain. The source domain, really, we're looking at providing one reference still per person. The target domain, we have an unlimited or abundant amount of video faces that we can exploit for design. So the context is the design of a pairwise matcher, and the objective is to generate a set of synthetic facial images to improve performance. And in particular, in this case, we're looking at generating augmented gallery images synthetically right at the bottom. Okay, so the challenges if you use something like 3D face reconstruction is that the images produced will not necessarily cover the full range of variations from the target domain. So we've been looking at exploiting GANs. Presently, the problems for our application are the lack of consistency and control of the outputs, and also the difficulties in preserving identity of reference images. So our system is based on, so it's a controllable GAN for cross-domain face synthesis. So essentially, there's two parts. There's a part where we're generating simulated face images based on a reference set rendered according to a certain pose, and then the second part is the CGAN, where we exploit these simulated images and target data to produce refined images. The next slide contains actually a more detailed view of the system that I'll just go over rapidly. So again, here on the left side, you have the 3D simulation that produces images, simulated images according to a specific pose. And then these are fed into the GAN that's right in the middle, the CGAN, which uses those images plus video, unlabeled video images to produce versions of those images as they would appear in the target domain. And right at the bottom, the third part, the attribute preserver, which is a novelty item for our system. Essentially, we have something that preserves pose and identity. Okay, so if you come to our poster, you'll see a lot of fantastic results. Here we have images generated with CGAN. We have also visualizations of distributions of synthetic images. We also have face recognition accuracy that's coming up. So we have results for face recognition accuracy as we grow the number of synthetic images, and also compared to the state of the art. So please come see the poster. Thank you.
So good afternoon, everyone. My name is Vítor, and I'm a PhD student at Notre Dame, and I'm going to be talking about the paper titled, Does Face Recognition Accuracy Get Better with Age? Deep Face Matcher said no. So previous works show that older people are easier to recognize than younger people, and those were pre-deep learning methods. And we use the largest available data set with real age metadata, and also 3 deep learning methods that are different. We split the data set into young, ranging from 16 to 29, middle, 30 to 49, and old age to conduct our experiments on this data set. We start analyzing by ROC curves, and the pattern here shown is contradictory to pre-deep learning methods, where actually old people are worse than younger. And we show for FaceNet, VGG Face 2, and ArcFace that they have a much different performance, especially with older matchers, FaceNet and VGG Face 2. In ArcFace, there isn't such big difference, but if you look close into the thresholds used, there is a difference into them. And because we couldn't compare with pre-deep learning data sets that were used, we also ran a traditional LBP matcher on our data sets to see if it was the CNNs that were doing this flipped pattern or was just the data set itself. And we showed that using the LBP matcher, we flip the pattern again. So older people are easier to recognize now than middle or young people. And my next slide. It's gonna come up now. We speculate that the problem is on the trained data sets because old persons in there have much less image. So we fine-tuned 2 models on young, middle, and old groups, but we saw no correlation between testing and between training and testing. So old group is always the worst, no matter what you fine-tune on. And we also trained from scratch on balanced data sets. And except from one result, we show that the accuracy for old people are still lower than middle and young. So in conclusions, we show that younger subjects are easier to recognize than older subjects, and that's for deep learning methods. What is driving the worse accuracy for older persons are the imposter matches. That's gonna be seen in my poster. Training data is apparently not the cause for this, and we didn't saw correlation between training and testing on age-specific groups, and a better loss function helps mitigating the problem. That was the case for arc phase. So we have a bunch more results that's gonna be shown to the poster, so if anyone is interested, please come and I can explain more details. Yeah, thank you.
Hi, Bertram from HKUST at ECE at HKUST. An appearance-based gaze estimator maps RGB images to gaze direction. The state-of-the-art uses deep networks. This paper describes an approach to low-complexity calibration based on a quantitative error analysis. Our method outperforms previously proposed approaches when the amount of calibration data is small, which is very desirable from the point of view of user convenience. Our method is only surpassed when the calibration data is too numerous for practical applications. We conducted an error analysis of a state-of-the-art gaze estimator. These figures plot estimated gaze versus the ground truth for different subjects. Perfect estimates follow along the black diagonal lines. We observe large subject-dependent biases. Over the entire training set, the mean between subjects squared bias exceeds the mean within subject variance. Thus, the primary source of error is the subject-dependent bias. Motivated by this finding, we propose a gaze decomposition method during training, which adds a subject-dependent bias to the output of a subject-independent estimator. Each subject's bias is learned during training by gradient descent. For calibration, we estimate the bias by averaging the difference between gaze estimates and the ground truth as the subject looks at a few different targets. This graph plots estimation accuracy versus the number of calibration targets. When the number of targets is small, our method outperforms all previous methods. Only linear adaptation, LA, shown in green here, exceeds ours, and only when the number of targets exceeds 32. In practice, few users would have the patience to look at this many gaze targets. Even without calibration, our technique results in state-of-the-art performance. This is surprising, since there is a mismatch between train and test. During training, we assume calibration, but this is not used during testing. To find out why this works, please visit our poster. Thanks very much.
Hello everyone, my name is Philipe Diaz, and this is our work on gaze estimation for assisted living environments. The population above 60-year-old is increasing at a very high pace, so there is a large need for methods that prevent costly interventions. But clinicians nowadays rely on assessments of mobility, activity of daily living that are at the doctor's office, very sporadic, and rely on questionnaires. So our goal is to use computer vision for an automatic long-term monitoring. If you break down the requirements, you need not only semantic segmentation, but also gaze estimation. For example, in those 2 scenes, we have the exact same elements, and from the gaze, we can see that in the first scene, we have 3 people chatting, 1 person eating, while in the second scene, we actually have everyone eating. So in this work here, we introduce a model that regresses gaze just from the facial key point positions. This model relies on confidence-gated units to disregard missing key points. And this model also provides predictions of its own uncertainty. For example, in case of backfill in green, you expect higher uncertainties. So this model relies only in the facial key points positions provided by the off-the-shelf open pose model. In case, the nose, the eyes, and the ears. Together with the key point positions, open pose also provides you the confidence of score detections. And from these inputs, our 4-layer network with only 283 trainable parameters regresses both the gaze direction and its own uncertainty of prediction. The confidence-gated units we introduce is to handle cases of missing key points indicated by open pose with a confidence score of 0. So you have simply a sigmoid that acts as a gate weighted by the confidence and a ReLU that shifts the input accordingly, similar to GRUs. Our results we first evaluate in the large gaze follow data set, in comparison first with a simple geometry-based baseline, and also the more complex gaze follow model, which is a complex network that looks at image saliency and also head features. And in short, we highly outperform the geometric model and perform on pair with the complex gaze follow model. And if we remove our confidence-gated units, performance drops when key points are missing. We also see that the prediction of uncertainty is high correlate to the actual error. So here we see in radial distance the actual uncertainty prediction, and most of the high error ones are mapped at far from the center. And then we finally evaluate our model in an actual discharge facility, a hospital illustrated here. And we see that our model highly outperforms the gaze follow model in these data sets, regardless of the cameras combinations, especially because the gaze follow model is heavily biased towards saliency objects, like the TV that the person is actually not watching there. So for more, please come see our poster number 31. Thank you.
Hello everyone, I'm Sandipan and I'll briefly talk about our work on hallucinating facial context and background pixels from a face mask. So research has shown that presence of facial context in face images actually improves face verification performance for both human radars and deep learning models. Now the facial context can be occluded when the subject is wearing hats or hoodies, and that can lead to false face verification results. Also, if you are generating novel views using 3D models for existing or synthetic identities, due to missing 3D correspondences for those pixels, you don't get valid facial context or background pixels. So how do we generate the missing pixels? So one way is to use off-the-shelf in-painting algorithms, but because they are not trained to hallucinate such a huge set of pixels, they generate unrealistic results. The other option is to take the face mask and actually swap it to a full face image using any face swapping algorithm. However, for that you need strong similarity in facial pose, gender, and ethnicity, which is sometimes unrealistic. Moreover, some of these face swapping algorithms are not generalizable and work for only one person at a time, like the deepfake algorithm we all have heard of. So we treat the problem of facial context hallucination in a different way. So because there are multiple plausible hallucinations that can be possible for a given face mask, we treat it like the image colorization problem. So for a given ground truth image, we take its face mask out at different resolutions, and then we train a pyramid of GAN blocks with the face mask at different resolution, so that it learns to hallucinate the ground truth at different resolution. And once the GAN blocks have been trained, we can take this pyramid with only the generators and feed it face masks of existing identities and also synthetic identities, and it should generate some novel views with valid and realistic looking facial context and background. And because we are generating novel views, we can use this data as supplemental training data, and that should improve our network's performance because we are getting more intra-subject variations. So now we'll show some qualitative results in the next slide, where we take images from LFW and take their face masks. And as you can see from the results, our model generates much more realistic looking results compared to other in-painting algorithms when taken off the shelf. And as discussed before, we have shown that using our model as a supplemental training data generator can actually boost the performance of a deep network model for face verification. Here we are improving the performance of the ResNet 50 model. So if you would like to know more about our multi-scale GAN model, the training data that was used and the loss function that was used, please visit our poster. We'll also discuss more metrics, more qualitative and quantitative results. See you there, poster number 32. Thank you.
All right, so this is a work from my student Arsim Bran. She was supposed to be here. Last minute she couldn't, so you're stuck with me. I'm going to wing it somehow. So the work is about generating realistic human eye images with the prescribed gaze direction. There's a lot of work in this area. A famous algorithm, SimGAN, for example, starts from synthetic eye images, where we can control the gaze direction as we want, and then generates images in a target domain using an adversarial network with an L1 loss component, with the idea that if the output, they will have the same gaze direction. However, there's a problem. You're comparing images from different domains, right? A synthetic image with a target domain image. And so differences between these images may be due to factors other than just difference in gaze direction. So we take a different approach. We input to the generator a ternary mask, which is like a proxy for gaze direction. We still have a generator that creates images in the target domain. During deployment, we will input synthetic masks to generate images. But during training, we start from images in the target domain. We use a segmenter to find the mask. And then we generate the image. Now, we still compare the output with the input with the L1 loss, but we're doing that in the same domain. So this comparison is legit. Now, the issue becomes one of designing a good segmenter. How do we do that? We start with synthetic images and masks, where you can control everything. We can design a good segmenter, but this might not work so well for target domain images. We still use that. Design a generator. Then input a synthetic mask to the generator, get an output in the target domain, and then we take this pair, synthetic mask and target domain image, to add to the data set of the segmenter for training. We do that iteratively. After 2 or 3 iterations, turns out we find a segmenter that works real well with target domain images, and we generate very good images. So how do we evaluate this now to make sure that the gaze direction is correct? In multiple ways, visually. We also extract a mask from the output to compare with the mask at the input. If they are similar, hopefully the gaze direction is also similar. We also use the images that we generate, starting from synthetic images, into the target domain with inheriting the labels so that we can use them to train different things like iris detector or gaze detector in the target domain without any manual labeling. And you can see the numerical results in the paper.
Hi, my name is Sobhan. I'm going to talk about boosting deep face recognition via distangling appearance and geometry. So this work is done at WVU. So what we try to do in this work is we try to have distangle the geometry and the representation of a face and use that in the face recognition. So during recent years, we have looked at large scale data sets. We have looked at different network architectures and different loss functions. But we want to add something to that. So the current problem with face recognition is about large number of classes, limited number of per class samples, and variations in the environmental conditions. The state of the art right now is a sphere face, so we're going to expand on that. So during the training, for each sample, we find a sample which is very close to that sample in terms of landmarks. We transfer the landmarks of that subject to that face to be very similar to the main subject. And then during the training, we use these 3 faces, the 2 actual ones and the one which consists of representation of one, appearance of one, and geometry of the other. And we add 2 loss terms, one for the appearance, one for geometry, to increase the recognition performance. And we adopt a sphere face and coast face on for this for this framework, and we can see that the performance of both these two, like state-of-the-art algorithms, is improved using this method. And we present the results on LFW, YouTube face, and Mega face. And the last thing that I want to talk about is we can use the exact same algorithm for knowledge transfer when we want to predict the attributes of a data set when a very limited number of faces have the attributes and the rest of the faces are not accompanied with the attributes. So this is, and if for any further question, please stop by our poster. Oh, the next one is mine too. Thanks. So the next presentation, you are still stuck with me. So the next presentation is about robust facial landmark detection via aggregation of ungeometrically manipulated faces. So landmark detection, when we have like very extreme poses, is a really hard task. So to solve that problem, what we do, we both manually and adversarially change the faces. We extract the landmarks from these new faces. Then we go back to the input domain, and we aggregate the landmarks that are extracted using some sort of normalization. So we use two models to manipulate the faces. The first one is changing the landmarks like using a fixed function. Then the next one is changing the landmarks using an adversarial training to change the ID. So, and for the first one, we use two different tasks. The first one, just changing the landmarks arbitrarily. The second one is changing the landmarks in groups, like when all the landmarks that belong to eyes go to the same direction. All the landmarks that belong to mouse go to the same direction, and on and on. So here we can see some experimental results. We have the landmarks on the first row. Then we have the manipulated faces, the landmarks that are extracted, and then on the last row, the landmarks after the aggregation. And the method that we use for the aggregation is if a landmark is changed drastically in terms of location when we go from the input domain to the manipulated image, that landmark has a higher weight when we aggregate all the faces we have used. So here we have the results on three main data sets: NME, 300W, and we have the results both on the challenging test set. We have the results on the common test set and the full data set. And finally, here we have the performance in terms of again, all three subsets of the data sets we have used. And for any other question, please stop by the poster. Thanks.
Hey, my name is Yoav, and I will present you this work by Yoav Shalev and Lior Wolf from Tel Aviv University. Lip syncing has many applications in viral video sharing app, television show, dubbing across languages, and more. In contrast to other existing work, we do not modify the audio, but modify the video by duplicating and dropping frames, which result in changes that are far less noticeable. We create a syntactic training set by dropping and duplicating frames, thus creating misalignment between the video and the audio. Each training example is a triplet, which consists of a video stream, an audio stream, and a sequence of indexes that represent the correct mapping. We employed the leap encoder proposed by Zhaokang and Zisserman. Each element within the video sequence is a temporal stack of 5 consecutive frames, and the temporal receptive field are 3 seconds at 25 frames per second. For the audio encoding, 20 time steps of 13 male frequencies bands are being used. The temporal receptive field is 1 second. We employed the same architecture as proposed by Zhaokang and Zisserman. The input to the model are asynchronized audio and visual streams. Both streams are encoded using the audio and the visual encoders. Then, for each visual encoding, we calculated the Euclidean distance with all audio encoding and create a sequence of vectors. The sequence of vectors is then encoded using recurrent neural encoder. The encoding is then going through an attention-modulated LSTM decoder. The decoder attends the encoder's output and predicts an index of the input video stream. We have a large set of experiments taking into account that every literature baseline is applied in a different way. First, we compare our method with existing literature for a single shift synchronization by up to 1 second. Next, we compare for a dynamic shift, where video frames are randomly dropped and duplicated. We are always more accurate and have much less error in the obtained shift. Next, we compare the MCD and the MCD dynamic time wrapping scores of our method and the method proposed by Albiero et al. For this purpose, we wrap the audio instead of the video. Our method outperformed the baseline literature. Finally, in order to quantitatively evaluate the performance of our method, we conducted a user study, which shows that our method can fool users to consider fake videos where one person is speaking while showing the lips of another as real. Thank you.
Good afternoon, I'm Anurag Chaudhary from Michigan State University, and I'm discussing today my work, can a CNN automatically learn the significance of minutia points for fingerprint matching? This was done in collaboration with the University of Salzburg. Now, fingerprint consists of ridges interspersed by valleys to form an oriented texture pattern on the tip of each finger, and ridge anomalies corresponding to ridge endings or bifurcations are called minutia points. And the spatial configuration of these minutia points have been assumed to be unique to every finger. Now, throughout time, we have seen that minutia points have been used extensively in both forensics and biometrics to perform fingerprint matching. So the question that we are trying to answer here is, can a machine learning system automatically learn the significance of minutia points for fingerprint matching? So basically, we want to verify if the domain knowledge that is gleaned from biometrics and forensics about the importance of minutia points, if it can be verified using machine learning. So what we do is we train a patch-based convolutional neural network, we'll see, and to automatically deduce features important for fingerprint matching. And the features deduced by the CNN, if they positively correlate with minutia points, then it would prove that the minutia points are actually important for the task. For this process, what we do is we work with pair of fingerprint images that we align using shift key point matching while ensuring no minutia points are used for alignment. And these aligned images are then tessellated to form genuine and imposter patch pairs. These fingerprint patch pairs are then used to train the proposed MDCN and CMEs network to perform patch-level fingerprint verification. Now, our experimental results show that for both baseline and proposed models, fingerprint patch pairs, when they contain minutia points, are actually matched at a higher true match rate, yield a higher genuine match score, and a lower imposter match score. So in essence, higher verification performance is observed whenever the patch pairs being matched contain minutia points. We use CASHIA and FVC 2000 datasets for our experiments. We also perform GradCam analysis of our method, which is to localize and find out where the network is actually looking at when it's trying to extract the features. And it turns out both the networks extract features from the vicinity of minutia points whenever they are present. And additionally, the proposed method also extracts features along the ridges whenever there are no minutia points there. This could be attributed to its ability for multi-scale feature extraction. So in conclusion, going back to the question, can we actually use a machine learning system to verify the importance of minutiae points? Yes, we can. Because both the networks, when they were trained, they were not given any idea of what a minutiae point is. They did not know the concept of minutiae points. Yet they converged upon minutiae points for extracting features when they had to perform the matching. Please stop by our poster. We'll talk more about it. Thank you.
Hi everyone, I'm Yannick, and today I want to talk about the work of Julia and my collaborator, Cynthia. So one thing we could do is take faces and then apply random transformation, and you can get funny faces from that. However, if you want to talk about caricatures, it's completely different. When doing caricatures, you want to amplify characteristic traits from a face. And usually, only artists are able to do something like that because you need to analyze the traits of a person. Recent literature has focused on automatic caricaturization, and one of the main issues is that you cannot ask for a single artist to generate 10,000 drawings to train a neural network. So that's just impossible, right? So previous state-of-the-art are using unsupervised method with a corpus of large drawings from different artists. However, the main issue here is that it's conflating the style and the warping, the deformation all together. You get a big soup of artist styles. In this work, we're interested into disentangling the warping, the deformation with the colorization, the stylization in the context of few-shot learning. How do we do that? So we forward our image into what we call a perceiver network. It's just a squeeze and excite network to obtain a small warping field, which we upsample. And then we pass through a warping module to get an image back. And then we can train this in an end-to-end manner. However, if we do that, it doesn't work, it doesn't converge. And our hypothesis is that the warping module doesn't get a strong enough signal for the gradient to train all the way up to the perceiver network. So what we do is we use a loss directly on the warping field. And after all of this, we can apply a stylization network, for example, in this case, cartoon GAN, in order to get a cartoon. So from those inputs, our method generates those warps and from those warping fields. And after characterization using caricature GAN, we can get this result. And here's the previous state of the art on this topic, which is warp GAN. And here are other results where from the input photo on the top row, our method can get the center row. As you can see, we get really close to the estimated characteristic traits amplified by the artist on the bottom as a reference. And also, in addition to that, we found a way to either tune down or amplify the warping fields that we can generate. If you want more information about all of this, come to our poster number 38. Thanks.
Hello, I'm Ratish Kalarod from Adobe, and this is a work on facial super resolution with Professor Fatih and Tavo from Purdue University. So this work is inspired from attention mechanism, recently very popular. So we use the facial attention, which is derived from parts of face to super resolve. The problem of face super resolution is to convert a low resolution image, as you see on the left image, to a higher resolution image, as you see on the right image. If you carefully look at the parts of the image, say for example, eyes and hair, a low resolution image does not contain much detail. So in this work, we try to address 3 parts. One is this is a patch-based method, which means that you can arbitrarily high resolution, super resolution images can be trained. Also, this has a multi-stage encoder to it. On this architecture part, one important part is where we convert the face image to facial masks and then feed that into a ResNet-based backbone to super resolve. In the middle of the network, we upsample and downsample. So talking about face parts, these are the facial parts used for attention. So skin and hair and other facial parts are segmented out initially, and then that is used for channel attention. So result from 256 cross 256 images, we can see leftmost is the input and rightmost is our result. It's pretty convincing. The higher resolution details are maintained in our work. Also presented is the high resolution 1024 pixel images. If you carefully look at the eyes and hair, we can see a lot of details are recorded from our method compared to other methods reported in the literature. Results, we consistently get about 2 dB of PSNR improvement across 256 cross 256 and 1024 images. And also on other metrics like PSNR, SSIM, MSIM, our method surpasses the state of the art. Speed of the network, we can run this network on a normal GPU, 1080 Ti GPU at 30 FPS, given the configuration, and the resolution of the image can be from 256 to 1024, arbitrarily high if you have more GPUs and compute resources available. Stop by my poster at poster number 39. We have more details and more in the poster there. Thank you very much.
Hello everyone, I'm Howie, a first-year CS PhD student in UCL1. Today I'm very glad to share our latest research, no parametric structure regulation machine for 2D hand pose estimation. As we know, there are many applications for 2D hand pose estimation like AR, VR, and GCI. However, compared with other pose estimation problems like body pose or face, hand pose is much more challenging because hand suffers from self-occlusion due to articulations, viewpoints, and objects. And recently, we noticed that some researchers conduct hand pose estimation and hand mask segmentation in a multitask learning way, which can improve hand pose estimation a lot. However, we know that mask annotation is really difficult to obtain, and there are only a few datasets contain both mask and key points. Thus, it leads us to think, can we get hand masks from key points? Well, the answer is yes. From this figure, we can see that there are 20 lines, or we can say line segment in a hand model. In our paper, we propose 2 novel line mask representations. For line determined string mask, we generate a 0-1 mask around a line. And for line probabilistic mask, we get a Gaussian heat map around a line. Well, furthermore, we can do line compositions. Here we propose 2 ways to combine. For G1, it means we collate the 20 lines together. Then we can get a whole hand mask. And for G6, we collate them into 6 groups. There are 5 fingers and 1 palm. This composition can give us more detailed structure information, as you can see. So what is NSRM? They are just some simple but novel hand structure representations, which all generated from key points without any annotations. As you can see, the LDM-G1 is a synthetic mask here. And the network of our paper is very simple, which is based on convolutional pose machine. We simply change the front stage to learn our structure representations and apply cross-entropy loss on it. Here we note that although we just try our structured representations on CPM, we believe that this module can be added to any other networks as well, like Hourglass and HRNet. And here is the qualitative results on panoptic hand dataset. Our proposed model can achieve a huge improvement on PCK compared with the CPM baseline. And here is some qualitative results. And you can see our proposed NSRM can handle many heavy occlusion cases. Well, that's it. Thank you. And my poster is 40. If you have any questions, please come here.
Everyone, my name is Shang Zhao. I will present our paper today. Due to the development of commodity RGB cameras, motion tracking becomes more accessible to general users. The most challenging part in motion tracking is to solve the misalignments between deformed model and partially captured scans. For single-view scenario, occlusion, fast motion, and non-optimal constraints are the major reasons that cause large misalignment and tracking failure. For multiple view scenarios, calibration errors and synchronization of camera shutters and interference nodes between cameras can make the misalignment even worse. We use the differential representation of the information field to address above issues. The canonical model is fused from static pose of scanned object. We sample volumetric embedded nodes inside the model and associate each node with a rigid transformation. The rotation part is parameterized at unit quaternion to reduce the memory and computational cost. Then the model is deformed by the weighted transformation from k nearest neighboring nodes. To formulate the regularization term, we first evaluate the relative transformation in the local coordinate of neighboring nodes. Then we analyze the rotational invariant net strain energy between each pair of neighboring nodes, and derive the analytic solution in terms of the relative transformation. Our regularization term is aiming at minimizing the total strain energy. Comparing with our method, the traditional ARAP regularization has three disadvantages. First, ARAP can only constrain the translation part of the transformation. Secondly, it cannot uniquely determine the deformation with sparse embedded node. Third, it usually chooses a single reference frame for all node edges in the graph, which is not optimal. As shown, the rotational term can regularize the torsional distortion on the left foot. We further cluster vertices of the canonical mode into tracked, occluded, and untracked regions. For each region, we use different tracking strategies. For tracked regions, we use the canonical frame as the reference. For occluded and untracked regions, we use the latest tracked frame as the reference. We also apply an L0 regularization to adjust the weight of the reference frame in joined regions. For multiple view setup, we choose the relative transformation from the latest tracked frame among all camera views as the reference for occluded nodes. As can be seen, our adaptive tracking strategy can solve large deformation, avoid error accumulation, and reduce tracking failure in the occluded regions. Results show that our method has better registration accuracy for large deformation scenarios. Geodesic-based features are designed to estimate correspondences, which are more insensitive to isometric deformation. We join embedded graph and depth image through aligned points, and then estimate geodesic distance in unaligned region based on the values pre-calculated in the overlapped region from the canonical model. This is because the surface connectivity captured from depth image is incomplete or ambiguous due to the surface occlusion or contact. As can be seen, PDA has fewer correspondences within a small window. The spatial-based method, KD and DT, may find incorrect correspondences. Our method can find more reliable correspondences. Our method converges to the better alignment with fewer iterations. Thank you very much.
Hello everyone, my name is Chen. I come from University of California, Irvine. Today I'm going to present my research work, GANs, the depth image guide, generative adversary network for 3D hand pose estimation. So first I want to introduce what the problem. First I want to introduce what is the paired and unpaired RGB and depth image. So paired and RGB and depth image means the pixel the depth map and the RGB image has a correspondent. So, but current state-of-the-art 3-hand pose estimator require paired RGB and depth image to train, but most of the datasets had either RGB or depth image. Only few datasets had both. So, how can we train with our 3D hand pose estimator with unpaired RGB and depth image? The answer is yes. So we has this GAN. So we has a depth map reconstruction module to reconstruct the depth map from the original image and combine with the original image to use a hand pose estimator to give you the 3D hand pose estimator. So the first the depth map reconstruction model, we use a GAN model to reconstruct the depth map from the original RGB image. And we're using the fully convolutional network to utilize as an encoder and takes RGB as the input and output the estimated depth map. And for the hand pose estimation module, we first using CPM as the 2D hand pose estimator. We're using the hand key point, and we use the Gaussian blur for the direct delta distribution as the ground truth of the heat map, and we train on, and after that we had a 3D lifting network, which we trained the depth axis to predict the value on the depth axis. So this network takes the heat map as the input and output the value of the depth axis. And the last part is the depth regularizer, which we follow previous work, and this part can be proved that really helps the 3D post, help training the 3D post estimator. So our experiment is designed as first we use the regression part as a baseline, and we using the depth regularizer, the depth map from our DGGAN as our result, and we use the true depth map as our output bound. The result shows our model has can be trained better with when compared with the baseline, but still a little bit okay.
So I'm Zhang. I'm going to talk about our newest key point detection framework, multi-view supervision by registration. So our input is a multi-view image string, and we output a key point detection of all frames and fields. The challenge is that we only have limited annotation, and we cannot train a generalized model. For example, for here, we only have 4% annotated image. So our approach includes three kinds of novel supervision. In temporal supervision, the track detection from frame T is utilized as supervision for frame T plus 1. And in cross-field supervision, we utilize the rule detection from two different fields should coincide on the same epipolar line. And to avoid using drift and occluded detection in temporal supervision, we include a visibility supervision to effective temporal supervision. So in temporal supervision, we just pass two consecutive frames into temporal pathway and get their detection. While detection of frame 2 can be warped to with the optical flow to supervise detection of frame 1. So in cross-field supervision, we pass two synchronized frames from two different fields into field pathway and get their detection. Then we convert their detection to the 1D distribution along epipolar line, and we compute the divergence between the two converted 1D distribution. So in visibility supervision, we pass two synchronized frames from two different neighboring fields into a visibility pathway and get their visibility detection. Then we compute divergence between two visibility detection. So here's the illustration of how temporal and cross-field supervision helps the key point detection in our framework. We did the experiments on a multi-data set. And here we have the quantitative comparison between our method and the deep lab cuts. So the trailing number after the method name represents the number of annotation. So we found our method performed overwhelmingly better than the deep cut with the same number of annotation. So here we have the qualitative comparison between our method and deep lab cut. We found a jump detection in deep lab cut experiment while we have stable annotation in our method with the same number of annotation. So if you're interested in our work, please visit our poster. Thank you.
Hello, okay, so I'm Raul, and I'm here to present the work done by my colleagues on the University of Trento because they couldn't come today. So this is about attention-based fusion for multi-source image generation. So this is an extension of this task, post-based human image generation, where we have an input image of a human in a given post, and we aim to generate an image of the same person in a target post. And a standard state-of-the-art multi-source image generation, we extend this task to the case when we have multiple input images. Our model can handle a varying number of input images. So we have different input images of the same person in different posts, and we generate an image of the same person in another target post. And the model learns to combine the different input images to extract the relevant information of them depending on the pose difference of the input images with the target images, the potential occlusion that may happen, or the image quality. Technically, this model is based on an attention module. Input images are inputted to encoders with shared parameters, and then this attention module learns to extract the most relevant features of each input image and provide them to the decoder. The encoder model future deformation in order to target to handle the pose difference between each input image and the target pose. And we also handle, okay, let's go to the results. So in the paper, we provide extensive of qualitative and quantitative results, but here I'm showing these two examples. We have 5 images of the same person on different poses, and we aim to generate this image in this ground truth pose. So if we use only the first image, we get this result, which is correct, but doesn't have a lot of details. But if we use the 3 first image in each case, we get this image which has much more detail. And if we use all the 5 available images, we further increase the details of the resulting images. And this model has another interesting feature, which is that we can also display the attention maps, which show which parts of the input images are more used to generate the output images. So that's all. If you are interested in the technical details, just you can come to the poster. Thanks. Sorry.
Okay, try again. Nice. So my name is Katerina Buitsa. I am a PhD student at Personal Robotics Lab at Imperial College London, and I'm presenting our work combining Kalman filters with conventional CNN pose-tracking methods to achieve real-time pose-tracking. So human motion tracking is generally done using either marker-based or markerless cameras or motion sensors like IMUs. These are also sometimes combined. The advantage of markerless methods is that there is no requirement for the subject to wear any additional like clothing or markers or sensors. RGB cameras are also readily available. In camera-based tracking, though, we often have incorrectly identified people or joints. We lose track of joints or even whole skeletons, and we often confuse joints between skeletons or left and right sides. So you can see this in the clip on the screen, even in the person in the middle. So Kalman filters are meant to assimilate noisy measurements into physical model. A Kalman filter is one method from statistical data assimilation. You have 3 components, so a dynamic system model, a series of known control inputs, and multiple sequential measurements. You then produce a weighted estimate of the state of the system from the predicted state and any new measurement. So in our method, the poses are taken from the existing pose estimation method once every n frames. For n-1 tracking frames, we then use optical flow to get an estimate of position and velocity. We match the current and previous skeletons for ID. The Kalman filter is then updated for a new estimate, and if there are any points missing, key points missing at this point, we can take a prediction from the Kalman filter. So the tracked pose sequences are cleaner and more consistent. You can see them on the bottom of the screen. The skeleton identified in the background on the top is no longer tracked as it pops in and out of view, so we don't trust that data. The people in the background are more consistently tracked and harder to see from a distance. The individual key points are tracked more consistently. The Kalman filter also allows us to speed up the existing algorithm, so we can bring analyzed frames per second above 30 frames per second. While the slower existing method analyzes 1 frame, we can run several frames through the Kalman filter. So here we show for 3 different methods how we track for 2, 5, and 10 frames without significant loss of accuracy and get them all above 30 frames per second, which we take to be real-time tracking. We have more quantitative results in the downstairs. So thank you for watching, and if you want more details, please either look at the paper or come talk to me at poster 47.
So hi everyone, this is Yuliang. Today I'm going to present our work, Reducing Foot Scale in Human Motion Reconstruction with Ground Contact Constraints. So given a molecular video, we aim to reconstruct the 3D pose and shape for each frame. This is the fundamental problem in computer vision, and it has a lot of applications. For example, character animation, virtual reality, or robot imitation learning. So given a molecular video as input, the first method is to do estimation on each frame individually. We can see that the reconstructed motion suffers from high-frequency jittering. The second method adds the additional post-processing step on top of the single-frame estimations for temporal smoothing. While it indeed reduces the temporal inconsistency, we can still observe severe foot slippage artifacts when we zoom in, which is called foot scales. So this work focuses on reducing such artifacts. Our core idea is that when the toes or heels are in contact with the ground, the velocity should be 0. We call it zero velocity or ground contact constraint. For the whole pop line, we first extract 2D and 3D poses for each frame individually. We then predict ground contact events from the extracted 2D poses using a deep network. Finally, we use the zero velocity constraint for post-processing together with the temporal smoothing objective. So let's talk about the ground contact prediction. Since there is no dataset available, so we create a new dataset our own. For the input representation, since it is hard to collect diverse training data, so a model trained on RGB frames is very hard to generalize. Instead, we use 2D poses estimations, including toes and heels, as our input. We then predict the ground contact events using a temporal convolutional network. Here are some predicted results from our system. We can see that it generates reasonable predictions for both indoor and outdoor scenes. So that's the first step. Next, we are going to talk about the motion reconstruction. Once we have the ground contact predictions, we can use it for our zero velocity constraint. We adopt a two-stage optimization strategy. In the first stage, we use a temporal smoothing method to get a good initialization. We then add our zero velocity constraint and jointly optimize all the objectives in the second stage. So here are some motion reconstruction results from our system. For the zoom-in regions, we can see that the proposed method indeed mitigates the foot scale artifacts. Thank you for your attention, and welcome to drop by our poster at number 48.
Welcome to the spotlight presentation of unsupervised cross-dataset adaptation via probabilistic A-model 3D human pose completion. I'm presenting this work on behalf of the authors from Indian Institute of Science, Bangalore. Prior works on 3D pose estimation rely upon availability of label data and underperform in presence of uncertainty such as occlusions. Secondly, they do not generalize to the in the wild data sets. We propose a self-supervision-based probabilistic A-model post-completion framework to generate plausible poses in presence of uncertainty and realize cross-dataset transfer of human motion representation across unlabeled videos. It's a three-stage architecture. In the first stage, we learn an image-to-pose embedding. To simulate natural videography found in the wild videos, we perform augmentations. We add a random vector to the motion encoding for handling uncertainty in partially visible frames. The motion encoder decoder is trained using fully visible frames of the label data, and then we introduce adversarial training as shown in the algorithm. We leverage self-supervision to enforce correspondences across different augmentation schemes for both partial and fully visible frames. We achieve cross-data set adaptation by using self-supervised and supervised losses on unlabeled and labeled data. So here we present the qualitative results where the first row is input video with augmentations. We observe that the ground truth pose sequence in the second row matches our full body predictions. We perform the PCA to show the generalizability of the learned motion representations across data set with diverse actions, and this shows that the model learns a common embedding space. We compare a method with 3 variants on MAT's dataset. The first, R SNO SS, is one without self-supervision. R SSA applies self-supervision on full body frames, and R SSAB uses partial body frames along with the full body frames and achieves state-of-the-art performance. So in conclusion, we present a novel method for probabilistic post-completion that disentangles uncertainty in natural videos, and we learn robust motion representations that achieve cross-dataset adaptation. And finally, we obtain state-of-the-art results on post-estimation tasks not seen in the training. Thank you. For more details, you can come to a poster.
Hello, I'm Dong-Hyun from Tokyo Institute of Technology. Today, I'm glad to present our lightweight human pose estimation network and efficient training method based on teacher-student learning. Human pose estimation techniques can be utilized in various fields such as interactive interface for AR/VR and human motion analytics. Previous method usually requires special devices such as depth camera or mocap suits. After the deep learning breakthrough, we can estimate human pose accurately even with a single RGB image. However, deep neural network rely on model scale and is not suitable for low-power devices. Furthermore, reducing parameters affect the accuracy, and this is a high barrier to train an efficient lightweight network. To solve these problems, we propose Movinect, a lightweight 3D human pose estimation network, and the efficient training method based on teacher-student learning. We design our network based on Vinect proposed by Meta et al. And reduce the network to only 1 million of parameters. For efficient computation, mobile net backbone and depth-wise CNN layers are used. The proposed teacher-student learning-based method is used to train the lightweight model efficiently. Our teacher model gives an extra loss by following mimicry loss functions. After the training, we only used student model, which has teacher's knowledge. Next part is evaluation. Even with small network scale, our network reached 97.3 millimeter of MPJP, and compared to the vanilla method, the proposed training method reached 40% accuracy improvement. In inference time benchmark, the network performs up to 160 FPS on mobile devices. Because of high performance on CPU, GPU can be fully utilized to the graphics rendering, and this is a great advantage for various applications. In qualitative results, the network trained with our method makes more accurate results. Compared to the teacher method, our network is learning faster on old mobile devices. To demonstrate our network's advantages, we implement a 3D avatar application learning on mobile in real time. Because of the network's low deployment costs, the network can be utilized in various ubiquitous scenarios such as body gesture-based object interaction and remote healthcare and more. And thank you for your attention, and someone who is interested in our research, please come to see a poster number 50. Thank you.